Well, hi, my name is Todd Morra. I'm a PhD candidate at Clemson University. I'm working with Carrie. So brief chat about my research interests. I like getting the geometry to do the work for me. I like using geometric information to tell me a lot about algebraic objects related to them. So I play with Stanley-Reisner rings quite a bit and simplicial complexes. So what I do, I start with any old simplicial complex generated by, right, of course, its facets on some vertex set. And then there's a nice bijection between the faces of that complex and the facets of another, where essentially each of these facets is carrying around some face from the original delta, as well as its complement, as denoted by some Greek variables, so or vertices. I've expanded my vertex set. As I want to do, these have a geometric realization that I'll carry around. So the facets are the shaded in triangles. This would be alpha, beta, gamma. Good. And then all of the say A beta, right? These are edges and so on. This has a nice boundary. Now this is defined using reduced simplicial homology, but with this geometric realization that we always have in this case that I've built, the boundary is exactly what you might want it to be. There's this nice outer ring. So a little bit of notation. I've got a simple polynomial ring. Here's the Stanley-Reisner ring with the Stanley-Reisner ideal. I'm going to take a dual inside of the ring and then look at its image inside of S. And you make note, there's a nice bijection here again. Taking complement of each of the facets in delta hat gives me a generator for this dual ideal. So what am I doing now? So based on some work by these folks, supremely helpful, we've got a nice minimal free resolution for both that dual ideal I and through a simple augmentation for S mod I, this ring. So all of the elements of delta hat, which are not in the boundary, make up some basis vector in my resolution. So for dimension reasons, all of my facets are included in that. There are 7 of them here. And then we go through likewise in higher homological degrees. So all the edges in the boundary are highlighted in red. And so there are 1, 2, 3, 4, 5, 6, 7 edges left to be basis vectors in homological degree 2. I'm suppressing a shift here, by the way. And then there are 2 vertices excluded from the boundary I can include here. Differential, to me, has a very Cazul feel. So if I look at the image of E sub beta, I add on all the variables I can, so alpha, A, gamma, and C, whilst still remaining in delta hat. And then I toggle by a sign. There's an ordering on the variables. I won't belabor that. And then in degree 1, it's the only one a little bit different. Every basis vector is mapped to essentially its complement. Again, toggled by a sign. So it's nice to have a free resolution. It's nice to have a finite minimal one. Particularly enjoyable to play with monomial ideals. What's nicer still is I'm working on writing down an explicit DG algebra structure for this resolution. So there's a lot to check on. Most of the time gets spent verifying the Leibniz rule. So this will be an update in my Champs talk, an update on a work in progress. We'll look at some of the products that we're able to compute. We'll talk a little bit about the rule and some of the challenges in the proof. We'll see you all there.